In this video, I'm going to be going over a basic implementation of a binary tree in Java and talking a little bit about what a tree is, what a binary tree is, and so on. So a tree is a type of data structure. It's not linear. And in a tree, each node can have children nodes, and each child has its own children. So it sort of branches out and creates a hierarchy. In this course, we're going to be focusing specifically on binary trees. It's a little bit more simple. Binary trees mean that one node can have up to two children. So it has a left and a right child, and so on. So in a binary tree, we call the node at the very top, we call it the root. So the root can have up to two children, and those will have children, and so on. Everything that doesn't have any children we call leaf nodes, and everything that has one or two children besides the root are called internal nodes. So in the binary tree implementation, first we have to create a node class. I've created a private one just for this class. This is a tree node class, and in the tree node we have a parent pointer, a left child pointer, a right child pointer, and we're using generics for the data, and the data can be any object that the user wants. So then I have my basic constructors that have the data, and the parent can be passed in, or just the data, and it'll initialize everything. So our whole tree is made up of a set of nodes. And in this, I'm going to go over some of the basic functions of a binary tree. One thing to note is that a binary tree is not ordered, which means it can become incredibly inefficient if it's put in a certain way, or it can be pretty efficient. It depends on the way the data is. So here I have my constructor and I have an iterator. So I'm going to link the iterator class so you can read up on it below the video. But basically it's sort of something built into classes and can help go through iterations, like when you write a for each loop. For example, for an array, it has like an iterator in the array that'll go through each element of the array. So next I have my size function, returns the size, is empty, returns if the tree does not have any nodes. And then I have my insert function. So my insert function takes in one item, and it will create a node, and then it will insert the node to make the tree more complete. So it will add it to the left on the highest level. So first it'll make the node with the item. If it's empty, it'll just point the root to the node because that's the only node in the whole tree. And if that's not true, it'll create a queue and add the children of the root into the queue, then remove them and check them to see if there's an open space for the new node. And then if there is an open space, it will add the node to the right spot and then fix the pointers pointing to the node and from the node. So basically having the queue in there and using that to check, make sure that you're doing a breadth first approach, and you will be adding it to the first node possible, the leftmost on the highest level. And then at the end, we increment size. So then my next function is a regular breadth first search, and it will return true if the item is found in the tree and false if not. So it takes in the item. If it's empty, it'll return false because there's nothing in it. And because it's breadth first, again, we're going to use the queue. It's going to make it so that we basically stretch out the whole tree in a line, and it'll make them so we catch each line by line. So again, it'll make the the queue, and it will add each of the nodes to the queue, and then it'll check it. If the node from the queue is equal to the data, it will return true, otherwise it will return false. So the next thing is a depth first search. It will take in an item, and my specific function also takes in the order. So if it takes in 1, it'll do a pre-ordered depth first search, 2 in order, and then 3 post order. So, and then again, same as before, it will return true if the target item is in the tree. So, as usual, if it's empty, it will return false because there's nothing in the tree. And then here it checks that what the user has called is a valid input, and if it's not, it'll just return false because you have to be careful when you're doing this. You have to catch for user and handling errors. And then if everything seems good, we call the recursive helper function with the root, the item that we're looking for, and what kind of depth first search we want. So my helper function will take in those three things, and it will call, it's recursive, and it will call itself with either the right or the left child, depending on the traversal method, and it will continue on recursively through the depth lay, going down the tree. So if we're doing the pre-order, that means we first look at the current, then we look at the left, and then we look at the right. So first we check current. If the current node.data is equal to the item, we return true. If the node.left child exists, we call depth search helper on the left child of the item in the order. If the right child exists, then we check the right child, the item in the order. And that's for when it's a pre-order. When it's in order, we do a similar thing, except now we're checking left current right. So first we check if the left child exists, and if it does, we call the depth search again. If the left doesn't exist, we check the current, and then if the current doesn't exist, we check the right, and so on, and it'll call it recursively. And finally, post order, left, right, current, we check first if the left exists. If it does, we call it recursively again. If it doesn't exist, we check the right. If it doesn't exist, then we check the current. And once it's all gotten through, if it's not in the tree at all, it will return false. Okay, so the next function is the delete function. It takes in the target object to be removed, and it'll replace it with the right and most bottom node to maintain completeness and balance. So in this function, again, if it's empty, we just don't do anything. If the size is 1, this means we only have the root. We set the root equal to null, and we decrement the size. It's a special case. For any other case, we're going to add everything to a queue. And starting with the root, we're going to add everything to a queue. And then we're going to do a check. So if the node to be removed is a leaf, it's just going to remove the node, and it won't do anything because because that maintains completeness, and it's not an issue we have to worry about. So when it equals the target, we set the current node to the rightmost node, and we call replace. So let's see, this is my replace function. So my replace function simply replaces an old node with a new node, so it'll take in 2 nodes, and it returns nothing. This is just basic node pointer manipulation, and we'll just find the nodes and switch them around. So we call the replace. And then for unconnected right nodes and the current node, we do all our fixes and then clear the current node's children. And then we do what we did before, and we add to the queue to maintain our breadth first. And in that, we used our find rightmost node. This is a helper function that finds the deepest and rightmost node. Again, it uses a queue to do a breadth first search. It goes all the way to the end and chooses the last node in the search, because that's going to be our rightmost node and the deepest. And then it will return that node. And finally, a regular Java function is the toString function. So essentially this just returns the tree in a string form, and I'm formatting it as a data pair, so parent, comma, data, and so on, and everything's enclosed with brackets. Yeah, so this is the binary tree in Java, and next we're going to learn a little bit about binary search trees.